Simulated annealing is a heuristic optimization algorithm inspired by the annealing process in metallurgy. Here's a detailed explanation. 1. Objective: simulated annealing aims to find the global optimum in a large search space. It's particularly useful for combinatorial optimization problems where the search space is vast and the landscape may have many local optima. 2. Inspiration from metallurgy. In metallurgy, annealing is a process of heating and then slowly cooling metal to reduce its hardness and increase its ductility. Similarly, in simulated annealing, the algorithm starts with a high temperature, allowing for random moves, like the initial heating, and gradually decreases the temperature, allowing the system to settle into a low-energy state, like cooling metal. 3. Key components. Initial solution. It begins with an initial solution to the problem. Temperature schedule. It defines how the temperature decreases over time. This could be linear, exponential, or follow other strategies. Neighbor function. It generates neighboring solutions by making small changes to the current solution. Acceptance criterion. It determines whether to accept a new solution based on its quality and the current temperature. Lower temperatures make it less likely to accept worse solutions, mimicking the cooling process. 4. Algorithm steps. Start with an initial solution and set an initial temperature. Iterate until a stopping criterion is met. Example: a maximum number of iterations or convergence generate a neighboring solution. Calculate the change in objective function value, often called energy. If the new solution is better, accept it. If the new solution is worse, accept it with a probability determined by the acceptance criterion and the current temperature. Decrease the temperature according to the temperature schedule. Return the best solution found. 5. Temperature schedule. The temperature starts high and gradually decreases over time, allowing for exploration of the solution space in the beginning and exploitation of promising areas later. The rate of temperature decrease affects the balance between exploration and exploitation. Rapid cooling may lead to premature convergence, while slow cooling may result in excessive exploration. 6. Acceptance criterion. The acceptance probability for a worse solution decreases as the temperature decreases, following a Boltzmann-like distribution. At high temperatures, the algorithm is more likely to accept worse solutions, allowing it to escape local optima. As the temperature decreases, it becomes increasingly selective. 7. Applications. Simulated annealing is used in various fields, including combinatorial optimization, machine learning, and scheduling problems. It's effective for problems where finding the global optimum is challenging due to a rugged landscape with many local optima. Overall, simulated annealing is a powerful optimization technique that balances exploration and exploitation by mimicking the annealing process in metallurgy, making it suitable for a wide range of optimization problems.